are structured to maximize transport. And I will tell you, oxygen, carbon dioxide only move by simple diffusion, into and out of the blood. There's no active transport, there's no facilitated transport, it's all simple diffusion. So just like with capillaries, because the lung is a diffusion organ, you would expect to find characteristics that are going to maximize rates of diffusion. In fact, when you look at the lung, and I draw my lungs like this, here's a trachea, here's a lung right there, that's my lung. It's not like a bag on a pipe, at the end of a tube. If you remember that goat lung we had, we'll get that goat lung, because that's really kind of cool. Get that goat lung. Pick it up.
What you need, run up there?
Yeah. And look, if I kind of hung out here, it's solid. Or it seems solid. It's not just a bag. What happens is, this stuff that feels a bit like styrofoam, this is all millions and millions of these little microscopic, spheres or bags, the alveoli. See, one of the factors that limits rate of diffusion is surface area, right? So if your lung was just a simple bag, the amount of surface area would be really small. Instead, if you take your lung and separate it, smooth it all out, you have several hundred square feet of surface area with air on one side and blood on the other. It's got a huge surface area. Also, distance. We've talked about distance, I think, a little bit. Its effect on diffusion. So again, high surface area. And this is true. It doesn't matter if it's a lung, a gill, insect's tracheal system. All respiratory structures have at least one thing in common. They have huge surface area. They're often complex, folded structures. That's to do nothing more than maximize the surface area with air on one side of a membrane and whatever you're using as transport fluid, blood, on the other. Gills are all folded up in plates, tracheal systems branch like crazy. Some things breathe through the skin, it's all wrinkly to increase surface area. Then the other thing to note is distance. Now right here, this is kind of enlargement of one alveolus, even bigger here. And the capillary density outside of the alveoli, where basically the pulmonary capillaries, which is where you would pick up the oxygen, you're allowing it to diffuse from the air in the alveolus into the blood in these pulmonary capillaries. There's so many pulmonary capillaries, it's almost like a sheet of blood just outside of the alveolus here. But this membrane right here, the membrane that separates the air in the alveolus from the blood in the pulmonary capillaries. That's called the respiratory membrane. It's something like 0.2 micrometers in diameter. It's really thin. Again, this is nearly soap bubble thin. This is partly why you don't want to get trash and debris down in your lungs. These will pop, almost like a soap bubble. They're really delicate. But the reason they're that delicate is because they have to be really thin. The closer you can get this distance between the air, which contains the oxygen, and the blood in the pulmonary capillaries, the faster the rate of diffusion. So these membranes in the lung, and the membranes in the wall of the alveoli, they have a huge surface area and they're really thin. So you got a bunch of oxygen on one side of this membrane, blood on the other. It diffuses through very rapidly. In fact, your ability to consume oxygen is not limited by diffusion. The lung is built so well, structurally, that you can actually diffuse more oxygen into your blood than you can use. The limiting factor for our aerobic capacity is not the diffusion of oxygen, it's actually the transport of the blood, the bulk flow or convective flow of blood from the pulmonary capillaries back to tissues. That's the weak point. We diffuse plenty of oxygen into the blood. And that's your little respiratory membrane. And so these alveoli, they're microscopic. They're really tiny. The wall of the alveolus is basically made of one squamous epithelial cell. We'll look at it in a slide. I've actually already posted it on Blackboard. But your lung, if you look at a section of lung, it looks like a spider web. Just these thin lines, which are the walls of the alveoli. So a simple squamous epithelium makes up the wall. That's why it's so thin. There are a couple other cell types I need to mention inside the alveolus. One, see this, reddish looking thing right here? That's a macrophage. Remember, a macrophage is basically a monocyte that's left the circulatory system. When they leave the circulatory system, they're much more actively phagocytic. Your lungs have a huge number of these, what are called alveolar macrophages. They're there because you inhale a lot of junk. Even with our filtering and everything else, you still get bacteria, things like that. You don't think tuberculosis down into your alveoli. The macrophages are there to mop them up, destroy them with pathogen. If they're organic, debris, they can, digest it basically. Also keep in mind, once debris gets down here, it's not coming back up. Once you get out of the bigger airways, there's no way out. It's stuck down there permanently. If it's organic, cell debris, pollen, that sort of thing, the macrophages can slowly mop it up and get rid of it. If it's inorganic, like asbestos and silica, that's it. It's down there and it's just stuck. So you have a bunch of macrophages in there, which are not really the wall of the alveolus, but you have a lot of them in there. Again, help fight off infections, clear out debris. Then there's another cell type here. It's like this little blue hedgehog thing here. It's got a couple different names. This diagram is calling it a great alveolar cell. It's also called a type 2 alveolar cell. These have an important function. And to get to that, I got to mention one other thing. Notice the inside of this alveolus, here and here. You see this light area they've shaded kind of, I don't know, what is that, light blue? Right there, all along the inside. That's basically water. It's isotonic, it's got some ions in it, but it's basically a layer of water. That has to be there. Again, this is epithelial, right, lining the alveolus. You have epithelia out here as well, right, lining your skin. This is dry, is it not? Should be. Something wrong, where you're sweating a lot. This is dry, but remember, the epithelial cells on your skin, they're striated. There's multiple cells. These outer layers of cells are dead. If you have live cells, they have to be kept moist. That's why, you pick up a frog and they feel a bit slimy. The reason for that, frogs breathe through their skin. Those cells on the outside are alive, so they must be covered with fluid, with moisture, mucus. It's because they're breathing through it. Well, that's like the inside of our lungs. You can't have it dry. If there were no fluid in here, these cells would be dead, your lungs wouldn't work, you'd be toast. So there's a thin layer of water, basically, saline, lining all of these surfaces. Now that creates a huge problem. That problem is related to the water itself. Water has a lot of what's called surface tension. You remember what that is? I referred to it in one, but probably early on I may not remember. How about hydrogen bonds?
Those are the weak bonds.
Pardon?
Hydrogen bonds are weak bonds.
It's okay, here, I'm holding that.
Hydrogen bonds are the weak bonds, right?
They are weak, but they're really important. Usually the example you'll see for hydrogen bonds, let's say here's a water molecule. Here's another water molecule. Here's another water molecule. Those are all your H2Os. And remember, these covalent bonds between hydrogen and oxygen, they probably refer to those as polar covalent bonds. Oxygen has a stronger attraction for the electrons, so this bond here represents a pair of electrons. But they tend to be sucked towards the oxygen. Oxygen has a fairly high what's called electronegativity, high attraction for the electrons. So these are not shared equally, which means the hydrogen end of this water molecule, if you drew an imaginary line, most of the time out here, there's just a proton. The hydrogen's electron spends 90% of its time over at this end. So these two hydrogens have they call it a partial positive charge. The oxygen, because it has extra electrons around it most of the time, has a partial negative charge. That ringing a bell a bit from Anatomy 1, they talk about polar covalent bonds. Anyway, the result of this, a water molecule has polarity. That's why it's referred to as a polar molecule. There's basically a partial plus at this end, the hydrogen end, and a partial minus here. So if you stick water molecules together, what do? They will interact. The partial positive charge on the hydrogen is attracted to the partial negative charge on oxygen molecules, oxygen atoms about water molecules. Just remember this, ring a bell, shake your head or something? Mm-hmm. This is what they call hydrogen bonding. Yes, they are very weak bonds. I mean, in a glass of water, when you pour out water molecules, you've broken billions of hydrogen bonds. They're very weak, but collectively they have some strength. So you have hydrogen bonds in lots of things, proteins, But water is a good example. And that's why if you took water, let's say, I don't know, 50 milliliters of water, and you removed all outside forces on it, what shape would it have? You've seen it, you just don't remember. If I take every outside force off of 50 mLs of water, what shape is it going to be? You ever seen them like in the space station or old space shuttles where they'll squirt some liquid out of the tube? What shape does it take up? A sphere, right? Hydrogen bonds pull the water molecules together. Water does not want to be spread out flat. The only way to be flat in this room is gravity pulls it down, and gravity is stronger force than the hydrogen bonding, so it does make it a little bit, flatter. But if you remove gravity, yeah, water will form a sphere. That's because of the hydrogen bonds. They want to pull all the water molecules together. Then, the hydrogen bonds don't let it roll out flat. It would be cool to have like an aquarium in the space station. You just put a glob of water on a pedestal and maybe round, a fish swimming in it, no walls. Anyway, squirrel. So a hydrogen bond, an attraction between water molecules. Now the reason this is a potential problem is your alveolus. It's basically a sphere with a thin layer of water inside. And it's open to the outside environment. There's alveolar ducts coming out of all these alveoli. Ultimately, you can follow these little tubes all the way to your external area. So it's not a solid ball. It's like a ball with a hole in it. And the problem you have here, this layer of water does not want to be spread out real thin. The hydrogen bonds want to pull it together. This is a force that tends to collapse balloons, water bubbles, alveoli. These water molecules are pulled because of the hydrogen bonding toward each other. So the water wants to make one glob, not a thin spread out sheet. And this can be, when you add it all up, it's a significant force. Have you ever got like two microscope slides or two pieces of glass stuck together with water between them? If you try and pull them apart, they don't come apart easily. You kind of got to slide them. That's the hydrogen bonding. They refer to it as surface tension when you're in the air-water interface. Like you have a glass or something, if you're really careful, you can take a needle and set it on the water and it floats. A needle shouldn't float in steel, it's down through the water. But the hydrogen bonds with surface tension are sufficient to support light objects, on the surface of the water. So here's a potential problem. The water wants to collapse the alveoli. If this were just straight up water in here, the amount of force it's exerting to push the air out and collapse the alveolus is quite high. In fact, it's so high you probably couldn't breathe. Your lungs would have a tendency to collapse. So the hydrogen bonding or surface tension in this fluid in your lungs is going to try and force all the air out. In fact, if you take a lung out of somebody's chest, it is completely empty. It will collapse. And as we'll see, an intact lung normally isn't. There's other opposing forces that keep it partly open. So the water, the surface tension of this water lying in the alveolus, will tend to collapse the lungs. If it doesn't collapse the lungs, it takes a huge amount of muscular effort to inflate the lungs. That's what these type 2 alveolar cells are for. They secrete something called surfactant. It works a bit like detergent, really. A surfactant can be a variety of different molecules, but what a surfactant is a type of molecule that will interfere with the hydrogen bond formation. It basically breaks hydrogen bonds. So you have these type 2 alveolar cells, or greater alveolar cells, and they're sometimes called surfactant secreting cells. They secrete surfactant, which comes in here, dissolves in this water, and what the surfactant does is it lowers the surface tension of the water. And this is critical. You can see how critical this is if you look at premature babies. If you go back like in the literature or something 30 years ago, and a baby is born 3 months premature, what typically happens? They die. The prognosis was horrendous. They wouldn't live. Why do they die? Respiratory distress. You see, if you think about it, when you're developing in the uterus, what's one of the last organ systems you're going to need? Your lungs. You don't need them till birth. So they're fairly late to develop. And these surfactant secreting cells are one of the later ones to mature in the lungs. So if a baby, decades ago was born 3 months premature, there was no surfactant. So their lungs would typically collapse. They couldn't breathe. If the lungs didn't collapse, the amount of muscular effort needed to just try and breathe and inflate your lungs was huge, and they would usually, succumb to some sort of respiratory distress. Now, a few decades ago, maybe about 2 or so, a little more than that, time flies, they now can administer surfactant artificially. So if a baby now is born 3 months premature, they can apply a surfactant. They either have an aerosol form or an injectable form. Once they started applying that surfactant, 3-month premature babies now have a much, much higher success rate. The survival rate basically through the roof compared to what it was. That's why. That's how important that surfactant is. Now, keep in mind for later discussions, the surfactant does not eliminate the surface tension. There is still some surface tension there, but it reduces it tremendously. So it makes it much easier to breathe. Without that surfactant, your lungs would have a tendency to collapse, and it would be just physically much harder to inflate them against that surface tension. So the alveoli, really thin wall, covered in fluid, it's got those surfactant secreting cells to reduce the surface tension. The capillary density is huge. Membranes are thin. So these alveoli and their associated pulmonary capillaries are shown here. They maximize rates of diffusion. So it's fairly easy for oxygen to diffuse from the air in your alveoli into the pulmonary capillaries. And of course, once the oxygen's in the pulmonary capillaries, now we're just back to the circulatory system. We'll transport it from the lungs back to your heart and out to the tissues and back. But anatomically, that's kind of all there is to do for the respiratory system. External areas, alveoli. Now we'll go over a few other structures here in a bit. We have to talk about some respiratory muscles and some characteristics of the rib cage, diaphragm, just the mechanics of breathing itself. But as far as what the air is in contact with, that's it. External areas, the alveoli, and that's it. Then the oxygen's going to be in the blood, and the rest of what we'll talk about will be the circulatory system. Now, the next thing I could look at, I can do controlled breathing or no, let's do gases. We'll drop down to what we need to look at next. Once we get this air, oxygen, in your lungs, we're going to move, like I said, oxygen by diffusion from the lungs into the blood, and in the tissues, the oxygen will move from the blood into the tissues. And as we'll see in a bit, carbon dioxide is moving in the same manner, just the opposite direction. But when we're looking at diffusion, we know there's a number of factors that affect rates of diffusion. Again, surface area, distance, temperature, molecular weight, that sort of thing. But one of the main things that affects the direction of diffusion and the rate of diffusion is concentration gradient, right? Like all things, oxygen or CO2 will move from an area where it's got a high concentration to an area where there's a lower concentration. The steeper that concentration gradient, all else being equal, the faster the rate of diffusion, right? All right. So we need to look at concentration a minute. And to do that, let me give you an example. Let's say we'll look at so the air in this room right now is about 21% oxygen. The rest of the X is volume percent. So, out of 1,000 milliliters, 210 milliliters are oxygen. The rest of it, almost all of it, is nitrogen. The air in this room is about 78% nitrogen. Now, nitrogen we're going to kind of ignore because it doesn't really do much physiologically under normal conditions. So most of the oxygen is nitrogen, 78%. 21% is oxygen. And everyone in here looks like they're doing fine. No one looks like they're in respiratory distress. No one's turning cyanotic or blue. So I'm getting plenty of oxygen. Now, let's say one of you might buy a lottery ticket. You won one of those like $500 million lotteries. And you're very generous and you decide to send us all on a field trip because you had so much fun with the tests in this class. So let's go on a field trip. And you decided to send us to Mount Everest. Now we all get in the plane, fly over the fall. Then we get a helicopter, rent it, and it drops us off at the summit, the top of Mount Everest, about 29,000 feet. So if we went from this room to the top of Mount Everest, what would happen to everyone in this room?
Oxygen levels.
You would die. Everyone in this room would die. If we went from here to the top of Mount Everest, we'd all die. We'd all be dead. So, what do you think the percent of oxygen is at the top of Mount Everest? Do you think it's higher than 21%? Lower than 21%? You're gonna guess?
Lower.
Lower? Lower?
Lower.
Lower?
What?
The volume percent of oxygen at the top of Mount Everest is 21%, exactly the same as it is in this room. But if we were at the top of Mount Everest, we would all die, and we would all die due to lack of oxygen. That's what would kill us. But then you look, oh, what the hell? They're the same, right? I don't know what you're thinking. Yes, volume percent is exactly the same. You count 100 molecules of the atmosphere at the top of Mount Everest, 21 will be oxygen. You count 100 molecules of air in this room, 21 will be oxygen. But at the top of Mount Everest, you're dying because of lack of oxygen. And here's why. It's the gas thing again. You know, I gave you a 1 liter container, 1 liter, and in this container I put a 5% sodium chloride solution, right? And I take another jar, it's also 1 liter, I fill it up with fluid, and this one is 10% sodium chloride. Now this is not a trick question. I give you these two jars, they're the same size, same volume. This one's 10% sodium chloride, call it jar B. This one's 5% sodium chloride. Which one has more sodium chloride in it? This is not a trick question.
What?
10%.
I got a jar here with a liter solution in it. That's 5% sodium chloride. I got another 1 liter jar here, liquid. It's 10% sodium chloride. Which one has more sodium chloride in it? A or B?
B.
5% or 10%? It's 10%. We know that. 10% sodium chloride has more sodium chloride per liter than 5% sodium chloride, right? Not a trick question. Now, what if they did the same thing with air or gas? I seal this up, I seal this up. In one of these jars, I put in 5% oxygen. In this jar, I put in 10% oxygen gas. Which one has more oxygen? This one is a trick question. The short answer is you don't know. This one has a higher percent, but it might have less oxygen in it. What are you talking about? It's true.
What is the percentage on the outside?
The what?
What's the gas exchange on the outside?
There's no gas exchange. These are now sealed containers.
Oh.
But here's what happens. All right. We are going to go on a hike. And we're not going to go to Mount Everest because we don't have that kind of budget, but we are going to go to Mount Whitney. Why Mount Whitney? Because I can do the math in my head, that's all. All right, Mount Whitney is at about, I think it's about 15,000 feet. Now we're going to start off at sea level. So right here is the ocean. Here's some waves. So we are at sea level. And we're going to go up Mount Whitney, which is at 15,000 feet. Sea level is at 0 feet, right? Now, what is the pressure if you're standing at the average tide level of the ocean on Earth? What is the atmospheric pressure?
700.
760 millimeters of mercury. This is your sea level pressure. You should know that. I'm not going to give it to you. You will need it later. So sea level pressure, that's kind of our baseline. Average sea level pressure on this planet is 760 millimeters of mercury. Now, what causes that? Well, above your head, there's several kilometers of atmosphere, right? The atmosphere, the gases in the atmosphere. Gravity affects those, and those gases are being pulled down by gravity. They're literally squashing your body. That's where the pressure comes from. There's literally this huge column of gas above you, kilometers of it, squashing down on you because of its weight due to gravity. Does that make sense? Now, if I go and I walk up to the top of Mount Whitney, is the pressure going to be the same there? No, we know that. When you go up in elevation, what happens to the pressure? It drops. How come? Because if you're at 15,000 feet, that means there's 15,000 feet of atmosphere below you now. There's a lot less above you. It doesn't push down with as much force. And it turns out if you measure the pressure at the top of Mount Whitney, which is why I use Mount Whitney, it's about 380 millimeters of mercury. Pretty much half of what it is at sea level. All right. Now, that doesn't explain why we're dying at Mount Everest yet, but we're going to get there. Now, what I'm going to do, when I go to the top of Mount Whitney, I'm going to carry a 5-gallon, no, let's call it a 6-liter plastic container with me. You know, I went upstairs where I have the manure rotting upstairs. That's what I mean. A container about that size, glass, rigid plastic, something like that. It's completely open to the atmosphere. It has a volume of 6 liters. Now, the pressure out here is 760 millimeters of mercury. And this is just sitting at sea level right with me right here. It's open. So what's the pressure going to be inside the container? 760 millimeters of mercury. Agreed? It's all open. It's just sitting there on the table. Pressure is equal. Now what I'm going to do is I'm going to take a balloon and I'm going to stretch it over the top so it is sealed. Now nowhere can get into this thing, nowhere can get out necessarily. It's going to stay in the jar balloon sort of chamber, right? Now if I look at the air in here, this is atmospheric air, so 21% of the molecules in there are oxygen. That's what 21 volume percent means. So I'm just going to make some red dots. I'm just going to put 10 of them in here. 4, 5, 6, 7, 8, 9, 10. Let's say those little red dots represent the oxygen molecules in my container. Now I'm going to take my container with its balloon on it, and now I start my hike. I go up, I go up, I go up, I go up, I go up. If I start out with the pressure out here at 760 millimeters of mercury, as I go up to Mount Whitney, the pressure is going to drop, correct? What's going to happen to that 6 liters of gas by the time I get to the top of Mount Whitney? This is Boyle's law. I'm starting off with 6 liters of gas at 760 millimeters of mercury, right? I go to the top of Mount Whitney where I know the pressure is 380. What's going to be the volume up there? Well, you know, solve for V2, which is the final volume. I'll divide both sides by 380. That crosses that out. Divide this by 380. That's going to end up being 760 divided by 380 is going to be 2 times 6 liters equals 12 liters. Does that make sense? As you reduce the pressure, because of Boyle's law, the gas is going to expand, agreed? And what you would notice is this balloon would get bigger and bigger and bigger and bigger until you now have a 12-liter system. 6 liters are in the jar, 6 liters are in the balloon. That's the 12 liters. It'll double in volume. Does that make sense? Now, as the gases expand, have you changed the number of gas molecules in this container? No, nothing's gotten in and out. What has changed? They just spread out more. Now, if we look at these 10 red dots representing oxygen, as the gas doubles in volume, would all 10 of these oxygen molecules stay in the jar? Or would some of them end up in a balloon? Yeah, about half of them. I mean, you're expanding double. So now you have, and the nitrogen would do the same thing. Does that make sense so far? All right. The reason I picked 6 liters here, your lungs, when full, are going to be around 6 liters. At sea level, when you have the air in your lungs, if you counted the number of oxygen molecules, and then you go up to the top of Mount Whitney and fill up your lungs, they're the same volume, but if you counted the number of oxygen molecules, there's only half. Right? When that gas expanded, even though on top of Mount Whitney, you still have 6 liters of air in your lungs, if you counted the oxygen molecules, there's only half the number of oxygen molecules available to pick up by diffusion, right? That's why you die at top of Mount Everest. The volume percent of oxygen is the same in a free atmosphere everywhere. It's about 21%. That's roundabout. It's like 20.95. We'll call it 21%. What changes is the pressure. And the problem is that's going to change the amount of oxygen available for gas exchange. The problem is even as the gas expands, it's still going to be 21% oxygen. That doesn't help us to know how much oxygen is available for diffusion. So we have to use different units. What we're going to use are some things called partial pressure. This is actually, if you look at it up in your textbook, you're going to refer to this as Dalton's law of partial pressure. I'm going to show you how to use it first, then I'll give you the definition for Dalton's law. All right. Dalton's law takes into account not only the volume percent of the gas, but also the pressure, because that's going to determine how much of the gas is available in your 6 liters of lung, right? Here's how you calculate it first. All right, all you have to do is really simple. It's just multiplication. Take the volume percent of the gas in question. Now, we're going to be dealing with O2. you should just memorize atmospheric air is 21% oxygen. Mathematically, 21% is 21 hundredths, right? It's 0.21. So you don't multiply by 21%, you multiply by 0.21. It's the same thing. Ring a bell from our math years ago. So 0.21 is, that's 21 hundredths, that's 21%. 21 parts per hundred. Multiply that by ambient or barometric or atmospheric pressure where you are. So at sea level, we'll assume this room's pretty close, it's going to be about that value. But to calculate the amount of oxygen available at sea level, just multiply them together. 21% times 760 is going to be 0, 6, 7, 0, 12, 14, 15, go 0, 6, 9, 5, 1, 2 decimal points. That's going to equal 159.6. The units are still millimeters of mercury. That is the partial pressure of oxygen at sea level. No one writes it like that though. You can just do this instead. The abbreviation for partial pressure, you usually see it written as P. And then the subscript is the gas. So people actually say it this way. The PO2 is, PO2, what are you talking about? PO2 is just a notation for the partial pressure of oxygen. You know, once you, if you're in a lab that works with respiratory gases and things like that, no one's saying the partial pressure is too long. It's PO2 or PCO2 or PN2, whatever. So in sea level air, in the open atmosphere, the partial pressure of oxygen is about 159.6. And of course, I forgot my units, which are millimeters of mercury. You will always calculate partial pressure by taking the atmospheric pressure times volume percent. You should know sea level pressure is 760. You should know the atmosphere is 21% oxygen, 78% nitrogen. Any other things I'll give you, like Mount Everest. You don't need to remember what the pressure is at Mount Everest. I think I know what it is, but don't quote me on Mount Everest pressure. But it's up high. Mount Everest is about 29,000 feet up. It's probably the highest mountain we've got, although there's some debate. I mean, K2 is the other one. But so Mount Everest, the volume percent of oxygen in the atmosphere at the top of Mount Everest is still 21%. But the atmospheric pressure at that altitude is like 220 millimeters of mercury. The atmospheric pressure is much lower. Multiply that together, 0, 2, 2, 0, 4, 4, 0, 2, 6, 4, 46.2 millimeters of mercury is the PO2 at the summit of Mount Everest, 46.2 millimeters of mercury. So you compare the two. At sea level, you know, we got nearly 160 millimeters of mercury. We're just a little more than a third of the available oxygen at the top of Mount Everest. That's why you die. While the volume percent is still 21%, the partial pressure of oxygen is 46. That's pretty much not enough to keep a human alive. Not for long, not without acclimation. We'd all die if we went up there from this level and without any adjustments or acclimation. Went from this room to Mount Everest, we'd all die from lack of oxygen. 46 millimeters of mercury. So that's the partial pressure. That's what tells you how much oxygen is available for gas exchange. Even though sea level Mount Everest is still 21% oxygen, the partial pressure at sea level is 159 or more, and at Mount Everest it's only 46, and that is not enough to maintain, a human. That's Dalton's law of partial pressure. The way you calculate it for any gas, you take the volume percent times the pressure. So if I wanted the partial pressure for nitrogen, you can calculate it. Nitrogen's not that important at sea level, but it's 78% times 760. That'll give you the partial pressure of nitrogen in atmospheric air at sea level. And so on, you go for any gas. These are the units you use to measure the concentration of gas so you know what direction it's going to diffuse. And all this does, you got the volume percent, that by itself isn't enough. It also relates to pressure and volume percent. So that partial pressure tells you where there's more oxygen. Much more at sea level, 159, versus what you got at the top of Mount Everest, 46.2. And I will tell you, humans are very poorly adapted to altitude. You cannot go to the top of Mount Everest without suffering death or permanent damage. Yes, people have gone to the summit. A bunch of doctors, I think in the 70s, did something called Operation Everest. They did simulated ascents to top of Mount Everest. They put themselves in hypobaric chambers, and even months after the study, they all had at least some measurable permanent brain damage. The small stuff you wouldn't notice in daily routine, but some of the reactions were off. They did all these tests before and after. We cannot live at 29,000 feet. Well, some people can make it to the summit. If you watch people, without oxygen going to the summit, man, if they're moving at all, they're like, woohoo! You can't do anything. And you're also working about 40% brain function. So if you're top on Everest, you're a moron. Doesn't matter what you started as, you're oxygen starved. That's why what litters the whole mountainside around Mount Everest and all those big mountains.
What?
What litters the whole side of that mountain?
Dead bodies.
Well, there's a few of those too. Oxygen bottles. They're not even watching when they don't go to the top of Mount Everest without supplemental oxygen. Now, think of it this way. If I take an oxygen tank and I breathe 100% oxygen, what's the partial pressure of oxygen at the top of Mount Everest? That would be 220 times 100%. That means the PO2 is 220. So if you're breathing pure oxygen, you're fine. But that's why you have to have the supplemental oxygen. Also, if you fly, it's been a while for me, but I used to fly all the time. And you'll get in and they'll show you this safety video, right? If the cabin loses pressure, big 747s, the big passenger jets, they're flying about Mount Everest levels, 29,000 feet. They're pressurized cabins. They're sealed like a submarine at a few thousand feet, so it doesn't matter how high they go. But if they get a hole in them, the cabin depressurizes to ambient pressures. Everyone in the plane will pass out and die, including the pilots. That's why if they depressurize, that's when those oxygen masks come down. And you're supposed to grab them and quickly start breathing on them, or everybody passes out. And if you're the pilot, you pass out. It's not a good thing. But that is partial pressure calculated for any gas. I'm going to ask you to do it at least 2 or 3 times, so make sure you can do it. You do need to know the volume percent oxygen in atmospheric air, 21%. That's just memorizing. Nitrogen in atmospheric air is 78, and you need to know sea level pressure is 760. Anything else I'll give you. We're going to be on some random mountain or
So
some other planet.
0.78?
Yeah, what was that second number you said?
Which one?
You said nitro something?
Nitrogen is 78%.
So 0.78.
Yeah, which is
Everything else is just a trace. Those are the two.
You said-
Nitrogen's 0.7.
Nitrogen
Atmospheric.
is 78% volume percent of the atmosphere.
0.78.
Oxygen
Yes.
21%.
Yes.
Traces of everything else.
Atmospheric air is
carbon
0.2.
dioxide? No.
Minimal. Point
26.
0.0.
He said 0.21.
point
Oh, okay.
3 millimeters of mercury, I think.
Yeah.
Atmospheric pressure at sea level is 760.
Atmospheric pressure.
Yes, at
Okay.
sea level is 760. 760 millimeters of mercury. Now, the definition you'll see for Dalton's law, I mainly want you to be able to calculate it, but I think the definition you'll see in your book will be, here's the way Dalton solved this. All right, if you're standing at sea level, there's 760 millimeters of mercury pressure on your body, right? That is literally caused by the gas molecules smashing into you. So the total pressure is 760 from all these gas molecules, nitrogen, oxygen, smashing into you. Well, if only 21% of the gas molecules are oxygen, you're only exerting 21% of that pressure. That's kind of the way he thought about it. So the total pressure is 760, 21% of it's caused by the 21 out of 100 oxygen molecules smashing in your body. Make sure you can calculate it. You will use this if you do any kind of gas work, respiratory work, blood work.
So what is
We'll talk
Dalton's
about
law?
partial pressures. And I will tell you, even in your blood, partial pressure is still how they measure oxygen. If you pull out an arterial sample of gas, it has a partial pressure of oxygen, or PO2 of about 100. So it doesn't matter if it's a gas in a gas phase, gas in a liquid phase, its concentration is always going to be partial pressure. So you can calculate partial pressures, right? Because on the next quiz, won't be on this coming exam, that's all hard. But the next quiz you have, I'm going to give you a question. I'm going to give you either the atmospheric pressure or the volume percent, or I'll use sea level and normal values. And I'll ask you, what is the partial pressure of, under these conditions? Like, you're on some funky planet. The total atmospheric pressure is 1,500 millimeters of mercury. and the atmosphere is 10% oxygen. What's the partial pressure of oxygen on this planet? Just do the multiplication, and you'll be good. Just make sure you can do it. That'll be at least one of the short answers, or sorry, one of the multiple choice on the next quiz and next exam. So there, give me a point. Open, now it's reset. So it's almost like, you can't trigger the voltage-gated sodium channels for a period of time after it's been triggered. There's a period of time where it's inert. It's permanently closed. That's the refractory period. So no matter what you do during that period of time, it's not going to open. You won't get a second action potential.
Okay.
And the period of time it remains inert is actually really long in cardiac muscle cells. It stays permanently closed for a much longer period of time, so you can't get sustained stimulations in cardiac muscle cells. It resets much faster, like an axon or something. Does that make sense?
Yeah.
A big deal. We throw all kinds of numbers up on the board. You kind of need to generate a little bit, but it's not really bad. I'm going to go through these numbers because I'm trying to get to a point at the end, the last of the gas loss. But all we're showing you on this diagram is just if you sample different areas in the respiratory, in the atmosphere, respiratory, and circulatory system, what would the actual amount of oxygen be from point to point? All these values are in partial pressure, because again, that tells you the concentration rate. Now, of course, what you'd expect initially, the highest concentration of oxygen is going to be in the atmosphere. The lowest is basically going to be in the tissues, because they're what's consuming it, right? So you have to have a concentration rate, highest to lowest, in order for oxygen to move by diffusion. So the general trend probably makes sense. The actual numbers, all right, this box here, we're going to look at oxygen first. In the atmosphere, we've already calculated it. If you take a sample of the air in this room, calculate its partial pressure for oxygen atmospheric air, this diagram gives you a value of about 159, and all the units are millimeters of mercury. Now, what we do with that air, we're going to take it from out here and go and suck it down into our lungs. So that's all we've done. We've taken the air from out here, moved it in here. And now we're going to take a probe, stick it into your alveoli, that's where the inspired gas is. Pull that gas out of your alveoli and measure its PO2. It's 104. Let me see if I can make that diagram bigger for you. I'll write them on the board as well. So here, we take that air from the atmosphere, that's its partial pressure, PO2 of 159, and we just go suck into our alveoli, and now the PO2 in the alveoli is 104. I just want to mention a couple things about this. This is terrible. All we have done is taken the air and inhaled it. Look at the drop in PO2. We've lost a third of the available oxygen just by inhaling it. That is really crappy efficiency. It's what I told you earlier. Oxygen, of 33% just by inhaling. Again, the higher the PO2, that means more oxygen. We've lost a third of the oxygen just inhaling the gas. All right, part of the reason for that, there's two things here. The big one is, again, we have tidal breathing. We're going to blow an old exhale there out. And it turns out your lungs, when you exhale, are not empty. After you exhale, normally, there still might be 3 liters of air in your lungs. That air is stale. It's already lost its oxygen by diffusion. So then when you inhale, you bring half a liter of fresh air, mixing it in with 3 liters of old air that's just stale and in your lungs. That's part of it. That tidal breathing is just inefficient. Bringing new and old, you can get rid of old air out the same hole, always causes mixing of the old and new air. You'll lose a lot of efficiency there. Like I said, plenty of oxygen in the atmosphere, so it doesn't matter. We seem to get by okay as we go. But that's a drop in efficiency, or a big drop in oxygen just by inhaling. The other thing that is kind of interesting to note is, I think I mentioned earlier, atmospheric air is pretty dry, right? But when you inhale, the air in your lungs is saturated with water vapor, right? It's 100% humidity. Water vapor is a gas. Like other gases, it exerts a partial pressure also. So you can have a PH2O. I believe it's 47 millimeters. Right now, it doesn't have much water vapor in it. But when you inhale it, you're adding water vapor. That's a substantial amount, 47 millimeters. That's taking up space. It's basically diluting the oxygen because the space now taken up by that 47 millimeters of mercury water vapor is space that oxygen can't occupy.